A quick review of percent error, or in other words, how good is your data? Well, if your percent error is under 5% or less, that's industry standard. You're in great shape. Clean up and publish your results in the nearest academic journal. This is a high school lab. I don't know that under 5% error is really going to be supported by the dusty old equipment we have in our cabinet perched on our wobbly tables. If your percent error is 10% or less, that's decent enough for a high school or even an undergraduate laboratory. You're in good shape. Clean up, write your lab report. If your percent error is between 10 and 15%, well, you had a few problems in your experiment. Make sure you identify those in your conclusion as you clean up and put your stuff away. If your percent error is over 15%, you're looking at something that went wrong. If it's over 20%, you're looking at something that seriously went wrong. If you have time, this is where you back up to step 3 and you redo the experiment. Figure out what went wrong and fix it. If you have soccer practice, play practice, and the bell is about to ring and you don't have time to come in at lunch to redo your whole experiment, a very large chunk of your analysis and conclusion should be devoted to explaining these horrible results. What went wrong? Why? Whose fault was it? No, wait, don't use that one. How to prevent it next time. Submit a proposal for what you do differently next time and why these results are not in line with accepted physics. Now, if you're looking at high quality data, if you're measuring universal constants, if you're looking at well-known international constants, or something where the actual value is widely accepted, if you're looking at the mass of the sun, the charge of the electron, the strength of the Earth's gravitational field, look at the number you measured in the lab and compare it to the actual value. You know it's the actual value. 400 years of physics around the world is not likely to be wrong. Take the absolute value, convert to a percentage. There is your percent error. Highlight, put a box around it, save it for future use. However, what if the actual value is not known? What if you're working with an in-house experiment or a local measurement of something unique to you, like the mass of your physics textbook or the speed of your lab partner? If you've got calculations, in theory, which are sound, but are actually based on data, and you're comparing that to a direct measurement, who's to say that the theoretical calculations are accurate? Your theory is based on your data. Your direct measurement is based on your data. They're both equally suspect. If you're working with anything where the actual value is not widely accepted, then there's no point in deciding whether your theoretical value or your direct measurement is the more accurate. They're both equally suspect, so take the average between them. Average your two values and put that in the denominator. Use that as the standard of comparison. Measure the difference between these two as compared to the deviation from them both. Take the absolute value, multiply by 100, there's your percent error. Now, what's wrong with this data? Percent error equals negative 0.4277321. Seriously? Seriously? First and foremost, percent error is called percent error for a reason. Never express it in decimal form. Please multiply by 100%. Error is a percentage. That is negative 42.77321%. Second, no one wants to hear your negativity. Junior year is negative enough as it is. Be positive. No one cares if your data is 42.7% high or 42.7% low. Either way, it is 42.7% off from what your experiment said you should get. This is ridiculously bad data. Stop and redo the experiment and take the absolute value next time. Third, speaking of 42.77321% data, unless your lab looks like this, there's no possible way you took 7 sig figs of accuracy. Round your percent error unless you are wearing a hat like this and can really back up your data with that 77321. This is 42.8-ish% error depending on how many sig figs you had. Either way, redo the experiment. Now, as long as we're talking percent error, we might as well mention uncertainty also. I'm measuring G, the strength of the Earth's gravitational field, whose accepted value is 9.8 meters per second squared, and here I am knocking around at 9.9. Oh no, I didn't get the accepted value. Oh, my data is terrible. Hold on, hold on. Take a look at the measurement uncertainty here. Measurement uncertainty shows you what the range of your data is. It is the layperson's version of what you'll do in statistics and call standard deviation. Look, this is good data. We were relatively certain we didn't have that much deviation. This is bad data. We can't actually measure the differential magnitude of the stars because it got cloudy and we couldn't see them. The uncertainty is off the charts. Uncertainty is generally calculated as the difference between your highest and your lowest data point averaged out. Our data here appears to have been between 9.75 meters per second and 10.05 meters per second. That's what this plus or minus tells us. Anything between 9.75 and 10.05 is pretty representative of our data, though the mean came in at 9.9. So if we are looking at 9.8 here, there is not much point in harping over the percent error on this one, because 9.8 is between 9.75 and 10.05, and based on this measurement uncertainty, it's within the range of our results. This isn't an experiment that has to be redone because the data was wrong. This is an experiment where the uncertainty needs to be tweaked to make it more exact, more precise, and get a better handle on what we needed.